Hello everyone and welcome back to another video. Today we will give a book review about this book that is written by David Bessis. This book is called Mathematica, A Secret World of Intuition and Curiosity. The book is an autobiography of the author. He starts to tell you how he started to do mathematics from high school days, through his mathematical career until his retirement from mathematical research, when he started to be more interested in applied mathematics and artificial intelligence and so on. I recommend to read this book because, especially for students of mathematics, because he tells you what is the feeling of doing mathematics. Because there are, as the author says in his book, there are many things that are not entirely transmitted in textbooks, like when you read a book of mathematical analysis or algebra. You cannot get the feeling of how did those mathematicians actually got the ideas, or how do they constructed this theory that is so deep, so profound, and has so many applications and so on. So this book is basically about how to conduct yourself as a mathematician. So it is interesting because of that, and it is also interesting because in the book there are many quotes about famous and very relevant mathematicians, like Grothendieck, for instance, and that also work on these soft problems, like where is the source of intuition for mathematicians, and questions like that. And the downsides of the book is like, in many cases, the author tells you that it's like he is very humble in many parts, but another times he's like bragging about his mathematical power, or I don't know, it's not entirely clear, but there's like some contradiction in the writing, like he's been humble at some times and he's bragging at another times. Like perhaps it is common behavior of mathematicians to be humble and to be proud of yourself at the same time, and maybe that is not a contradiction. Perhaps it's very likely so. That will be the only down part. Well, there are also parts of the book that are not like entirely totally interesting to read. Like for me, the best part of the book was the beginning and the middle. Like in the last pages, in the last third of the book, it's like I wasn't totally into it, because in the last third of the book, the author starts to be more concerned about another topics, like artificial intelligence, biology, and things like that. But as I said, the author is not an expert on those fields. So the things that he can tell you about those fields are not like not of the highest level. It's just like beginner level biology, beginner level artificial intelligence scientists, and so on. So it's not like so there are better books to read about those topics than this book. But for the first 2/3 of the book, in which he tells you about the soft skills of mathematicians and so on, it is very worth your time. So I think students of undergrad mathematics, master degree students should read this book. In the middle of the book, the author discuss how is different the mental processes that go in the head of the mathematician when he's writing a proof, and how that thinking, that formal logic thinking, is different from the mental processes that are in the head of the mathematician when he's thinking about the proof. There's like some body of mathematics that is very standardized. So we move in that body when you write papers, but when you're doing research, like you're in another place that is freed from all of those things, in which you can think freely and imagine the ways in which you can make sure that something is true. And so there's a difference, and when you get that feeling, that intuition, you can go back to the standard body of mathematics and construct something that binds this result to that already existing body of mathematics. And so it's like there are two different minds in a mathematician. One is formal and rigorous, and another one is free and artistic. And in the books, in the textbooks, you are only taught about this first mathematical mind, but there is another one that is full of intuition and artistic inspiration that actually makes you, helps you to prove the most difficult and the most abstract theorems, and that type of mind can be fostered, can be make stronger if you do some kind of exercises that the author actually tells you how to do. When you are studying mathematics, you can like get your mind very I don't know how to say it exactly the word, but it's like very encased or very in a box. Like you read the theorems and you read like theorem 1.4.1, and then there comes the corollary 1.4.2, and so everything is very structuralized, and you can really get a feeling on how these things are linked between one another, and how these things are related to another theory. And because it's like a very spatial thing, like there are relations that are in the space, and some theory is here and around in the neighborhood of this theory, and there are the corollaries, and there's an interplay like that. So when you read the books, the textbooks, you don't get a feeling at all, because everything is linear, everything is a logical thing, and there is no room for intuition, there is no room for curiosity. Everything is given, and you are kind of a passive reader of the results. And in that way, I think you cannot hope to develop your ability to do new mathematics. This book also tells you lots of things about that, and how you can overcome those difficulties, those challenges, and make your work more innovative. And at the end of the book, he discussed the difference between, or not the difference, but the interplay between formalism and intuition through an historical example that was the relation between Hardy and Ramanujan. So this is the end of the book, and it is very on point also, because and you can read that in another book about Ramanujan. But Ramanujan was a mathematician genius that imagined theorems and very complex formulas without the need of formalization, mathematical rigor. And Hardy, on the other hand, was a mathematician that went through the classical educational system of UK, and although he was a successful mathematician, he wasn't at the level of Ramanujan. And at the end of the day, it made you think that formalism perhaps is not a necessary characteristic of mathematics, but it is necessary for the communication of mathematics, because Ramanujan knew the formulas in his head, but how could we be sure that those formulas were right? For Ramanujan, they were right because some goddess told him that those formulas worked. Like it was a divine information that he received in a dream. So for him, that was very, very real, and that true. But for the rest of the mathematical community, there was no way to know that those formulas or those theorems were correct, were right. And so there's where formalism comes into play, and it is the only way in which the community can accept a mathematical result simply by checking the logic that shows how this theorem is a consequence of another proven result of mathematics. And that is also interesting because for the most part, for most of the mathematical instruction or teaching, we are taught that the formalization or the formalism of mathematics, all of the little symbols are mathematics. Like if you don't use those symbols, you are not doing mathematics. But Ramanujan tells you another story in which you can use your imagination, your intuition to do mathematics without the need of any of those symbols of formalism. So that's my read on that history. And well, David Bessis gives you another interpretation of that you can check in his book. So that is for today. I hope you liked the video, and I hope that you give this book a chance. And if you want me to cover and to make a book review about another one, it can be either a soft skills book of mathematics, or it can be a textbook of mathematics that you want me to cover. I can read the comments and make some content about that. So see you around in the next video.